Hello everyone and welcome to this video presentation of our project. The project team members are Sathyanarayanan.V, myself, Annamalai.E and Sumanth.G.V. The contents of this project demonstration are as follows. First, have a look at what we learned through this Emertxe internship. All these days or for the past month, what all have we learned and what is the journey that we went through. Also, we have a look at the basics of C, and within that, as a sub point, we have a look at the comparison between C and embedded C. We also have a brief look at why we choose to use the programming language of C for all these embedded applications. We have a look at the embedded system and its applications. We have a comparison between a microprocessor and a microcontroller. We also give a brief intro about the microcontroller that we have chosen to use in our project, that is a PIC16F877E. We will have a brief look on the on-chip peripherals that are incorporated in the PIC16F877E. Then, finally, we'll move to the final act of this demonstration. It is the simulation of our microwave oven project. We will have a brief look at the project introduction and the software used. So, what was the journey and how did it go? At first, we all received an opportunity to write a test and get in for this internship. We all wrote a test for, I think, which I remember to be 90 minutes of, and it was all about the basics. We wrote the test, and of which, I don't know how many members have written the test, but 1,000 of them got selected and received the offer letter. It was one lucky moment, I say. Then the internship started, where at first, for the first 6 days, we were taught the basics of C. Yes, complete basics, and it was as if we were learning from the scratch. We went through everything. Like, let's say, you just name it. It's variables, data types, identifiers, keywords, structures, pointers, arrays, how to define a function, what are the types of functions, functions with arguments, without arguments, inline functions, so on, and so forth. That's how it went. Now, let me showcase something that I have learned. So, C. C is a general purpose programming language which is widely used for design of desktop based applications, OS designs, and also for games. So the main features of C languages, it includes low level access to memory and uses simple set of keywords. So the keywords that are used are simple, like printf, scanf, you can name it. And the style that we use for the programming is very clean. It's simpler to understand and it is easier to manage.
And as we discussed about C and their basics and given a just outline about C, and now we are going to ask the question, why C is used for embedded systems? And you want to know it why? And give a 5 reasons, good reasons about why you are using C programming for embedded systems. 1. Processor independent. 2. Portability. 3. Performance. 4. Bit manipulation. And 5. Memory management. We'll go through one by one briefly. Let's take processor independent. C language is not specific to any microprocessor or microcontroller or any system. It can work on various hardware configurations. 2. Portability. It's a vital option because we need to take the same code to any other hardware so that you can use it in any other PIC like that, so that you can debug or manipulate the code. In this, C is a medium level language. It can be manipulated and debugged easily rather than the high level languages. 3. Performance. C code gets compiled into a raw binary executable which can be directly loaded into memory and executed. Most of the high level languages rely on libraries, hence they need more memory, which is a major challenge for the embedded systems. And number 4. Bit manipulation. C is more flexible. Using bitwise operators, like if in a situation we need to handle the registers in a bitwise manner, like we need to read a data or write a data, we can use a C program which is very easy and flexible to access each bit rather than the high level language. It is very complex to access them. And number 5. Memory management. It provides direct memory control without sacrificing benefits of high level languages. And it also provides directly access memory using pointers. And when memory requirement is not known, we can allocate the memory dynamically. If the memory allocation is known, we will do it in static manner. These are the 5 reasons why we use C for embedded systems. And now we'll see a small comparison between C and embedded C. As we discussed about C previously, C is a general purpose programming language which can be used to design any type of desktop based applications. And about embedded C is an extension of C language. It is used to develop microcontroller based applications. And it is very easy to read and modify C language. It is not easy to read and modify the embedded C language because it has many lines of codes and it's tough to read every lines and debug them. An application of C program is logical programs, system software programs, and we also create some game applications with them. Applications of embedded C program is DVD, television, digital camera, and now we are going to see about a microwave oven in coming slides.
Let's go to the next part, embedded system and applications. So what is an embedded system, you might wonder? An embedded system is the combination of hardware and software incorporated into one to serve a special function. So let's say, for example, a washing machine. It has hardware components and also software components. There will be a few buttons if you might have seen. So whenever you touch a button, it is programmed to do a specific function. That's a combination of hardware and software incorporated into one to serve a function. Let's have a look on what is the difference between a microprocessor and a microcontroller. So microprocessor does not have any of the on-chip peripherals or any external devices like let's say a timer or a RAM or external memory, etc. A microprocessor contains an arithmetic logic unit, interrupt circuit and control units, while a microcontroller contains all these on-chip peripherals that I just spoke about. It has timers, it has LEDs, it has capture compare modules, it has so on and so forth. And then when we come back to the microprocessor, it has multiple instructions, it has many commands, it has a certain set of instructions that needs to be so specific to execute a certain task. But when it comes to microcontroller, it's not the case. We have only one or two instructions to move a data between a memory and CPU, while in the microprocessor there are multiple instructions. In the microprocessor there are multiple instructions. Like let's take 8085 microprocessor for example. So when to move certain data from a certain register to a next destination register, we have to use a command like move a comma b, we have move a comma m, we have move m comma a, and so on. While in microcontroller, that's not the case. So microprocessor system requires more hardware because it does not have any of the on-chip peripherals. So it will lead to an extended size of the PCB in which we are going to design a certain application. While in microcontroller, the PCB size is going to be very small because a microcontroller already has all those peripherals inside it. There are not much pins that are multifunction in a microprocessor, while in a microcontroller, the same pin can serve multiple purposes. Like for example, the port A in a microcontroller also serves for the purpose of analog to digital conversion. And then when we come back to microprocessor, it has only 1 or 2 bit handling instructions, while in microcontroller there are many bit handling instructions. So let's talk some more about the microcontroller that we will be incorporating in our project. It's the PIC16F877A microcontroller that we'll be using in our project to simulate the output. PIC16F877A has multiple on-chip peripherals. Like I said before, it has 5 ports, it has 3 timers, it has LEDs on the development board, it has a capture compare modules, it has analog to digital conversion, it has a comparator, and so on. Let's have a look at some of the on-chip peripherals and some peripherals that we will be interfacing in our project, and let's have a brief look at them. So some of the peripherals that we have interfaced with the PIC microcontroller are LED, CLCD or character liquid crystal display, timers, tactile keys, and interrupts. Let's have a look, shall we? So LEDs. What's an LED? Light emitting diode. It's an external device that is connected in the microcontroller development board. Its output is blinking, and some of the features of LED is going to be that it consumes less energy, it has longer life, it is smaller in size, it is faster, and it costs very less. So if we move on to the CLCD, that is a character liquid crystal display, it serves the purpose of displaying ASCII characters. We can access an CLCD in 2 modes. The communication can be established in 2 modes. One of them is a 4-bit mode and another one is 8-bit mode. Moving on to the timers, there are 3 types of timers that are inside the PIC16F877E. The timers can be used as counters or for PWM pulse width modulation generation. So let's have a deeper look into the timers. Timer 0. Timer 0 is an 8-bit timer. It has a software programmable prescaler, and it can be used as a timer or a counter, and it is also readable and writable in nature. Timer 1, on the other hand, is a 16-bit timer. It has two registers, TMR1L and TMR1H. TMR1L is for saving the least significant bit or data of the timer, and TMR1H is for saving the most significant bit data of the timer. And then together this register passes as a 16-bit timer. It is also readable and writable in nature. It also has a software programmable prescaler. Moving on to the timer 2. Timer 2 is quite different when it comes to the other two timers. It is also an 8-bit timer. It has a software programmable prescaler, while also it has a postscaler. It is also an 8-bit timer, and it is also readable and writable in nature. Timer 2 has a certain period register. The period register stores a certain value, and it will count from 00H to the value of the period register. It will go into overflow mode once it reaches this period register value.
Now we can move on to the next topic, that is tactile key. And a tactile key, which you all know about, is a simple switch. It is used to allow the electricity to flow in electric circuit by manually pressing the operating section. The operating section, which is visible in this image, that is a button like that knob on the top of this image. When we press that, electricity is passed through the circuit, and we release it, it stops. Now let's go to the next topic, matrix keypad. Now you may wonder, why are we using matrix keypad? Here is the reason. When we need to give more inputs and also save the number of control lines, here comes the matrix keypad to do both jobs at a single time. It also uses the same concept like rows and columns. It is a matrix type, and this we are come across in our day-to-day life, like using telephones, calculators, digilockers, and many other applications. Now let's see how the matrix keypad works. Okay. The microcontroller sets all the column and row lines to the input. Now, the microcontroller sets the row lines at 4 lines to low, that is ground. After that, it checks the column lines one at a time. If the column connection stays high, the button on the row has not been pressed. If it goes low, the microcontroller knows which row has been set to low and which column has set low. Finally, it knows which button has been pressed and corresponded to the detected row and column, so that the input has been passed to the code. Now let's discuss about interrupts. Interrupts plays a vital part in the microcontroller. Okay, an interrupt is a signal to the processor emitted by the hardware or software, indicating an event that needs to immediate attention. Whenever an interrupt occurs, the controller completes the current instruction and goes to the interrupt service routine to complete the request sent to the CPU. This is what happens in the interrupts. Okay, the interrupts can be either classified into hardware and software interrupts. Now let's take a brief look on it. Hardware interrupt. A hardware interrupt is an electronic alerting signal that is sent to the processor from an external device or external peripheral device. For example, take a keyboard and pressing a button and giving an input to the CPU, and it takes the input and process that request. And like that, let's say about software interrupt. A software interrupt is caused by either exceptional conditional or a special instruction in the instruction set which causes an interrupt when it is executed by the processor. Now let's discuss about interrupt service routine (ISR) and the steps to execute an interrupt. An ISR, also called as interrupt handler, is a software process invoked by an interrupt request from a hardware device. And let's see the steps to execute an interrupt. Whenever an interrupt gets active, the microcontroller goes to the following steps, which are: the microcontroller closes the currently processing instruction and stores the next instruction address into the program counter into the stack. Now, the interrupt request is accessed and it goes into the interrupt service routine through the interrupt vector table, and it acquires the address from the interrupt service routine and jumps to the interrupt service subroutine to access the request and execute them. After the execution of the interrupt request, and come back to the stack and pops the program counter address to find the next instruction and execute them. This is how an interrupt is executed.
Okay, let's get started with the project. The project title is Simulation of Microwave Oven using PIC16F877A microcontroller. A micro oven is a small device which we use to heat or preheat the food to make it warm or hot. Its main principle is to emit high frequency electromagnetic field inside it to make the food heat. There are four cooking modes such as micro, grill, conduction, and start mode. So we have used some of the software such as MP-Lab.XID, MP-Lab.XC8 compiler, and PiximLab to implement in this project. MP-Lab.XID is nothing but a freeware integrated development environment uh, for development of embedded applications in which we have built the code and are, run the code. In MPLab C8 we have the compile it compiles the code and it generates the hex file in it. In PiximLab we have loaded the hex file and visually seen the output of the project. So now I will demonstrate the project. Let's get started with the code. I have used a MPLabX IDE to build the code. I have called the functions such as CLCD, matrix keypad, timer, and ISR functions. These have been discussed by my teammates earlier. I'll just say what it is and what function it will perform in my code. CLCD. It is a character liquid or crystal display which displays the character in it. I have added characters like my four modes: micro, grill, convection, and start mode. Then later it shows time in minutes and seconds, etc. Then ISR, it is a interrupt service routine. It is a process invoked by an interrupt request from a hardware device and sends it to CPU, interrupting the active process. Then matrix keypad, it has a 4 into 4 that is 16 key buttons on which we will give the input. From the 16 key buttons I have used 9 buttons for this project. So I have given if else ladder in which I have given conditions like if I press this button, this thing should happen. For example, if I press 1, it should go to micro mode, like that. It takes input and gives the output accordingly what the input is. Timers, it just controls the timing operations in the microcontroller main function. I have given all the functions here. So now I will build the code. So it has been built successful. The XC8 compiler will generate a hex file in my project location. Now let me demonstrate the output which has been simulated in the PiximLab. In PiximLab I have to choose my board. I will go to PickGenius and give my microcontroller as PIC16F877A, and I will just load my hex file in my project location. So as I stated earlier, it shows powering on and micro oven is on, and then my 4 modes are being shown. So now I will go to my micro mode. I will press 1 and it shows the power as 900 watts which have been given in the code. So it's asked me what time should I set in minutes and seconds. So I will give like 5 seconds and enter it. So it will run for 5 seconds. After the 5 seconds is over, a buzzer will be turned on and it shows a cooking timer sub which I have been given in the code. It's the micro mode. Then it again resets to initial condition and shows my 4 modes. Then okay, then I will give the grill mode. It is same as the micro mode. It asks me to set time seconds. Again I will give like 3 seconds and enter it. It again runs for 3 seconds and the buzzer will be turned on.
Again resets to initial condition. I will go to convection mode, which just starts to preheat the oven. So I will it asks for temperature, so I will set the temperature as of 180 degrees and enter. So it shows the 60 seconds. I think it takes some time, so I will just change the code. So here it is. I will just give for about 15 seconds and I will build it again. So build is successful and hex file is loaded. So I will just reload the last hex file. So I will go to convection mode. I will set the temperature as 180 degree again. So the time starts as 15 seconds. So after the preheating is over, after 10 seconds it will go to micro mode and or grill mode. It is used for baking stuffs or heating the food extra. So the preheating is over, so it again shows me the time. To set time, so I will give like 3 seconds. So it will start for 3 seconds and later it buzzer will be turned on. Again it will be resetted to the initial condition. I will give the last mode, that is start. It goes for 30 seconds. If I again press 4, it adds 30 seconds to the oven. You can see it. Then later if I give 5, that is it passes the oven. The work will be passed. Then if I want to resume the task, I have to give 4 again. It will be resuming the task. Then if I give RB3, it will the door will be open. The message will be shown, you should close the door, and the buzzer will be turned on until the door is closed. I will demonstrate it now. So it is the work is done. So after 40 seconds the buzzer will be turned on and the cooking time is up. It will be shown in the CLCD monitor. So I will just stop the condition because we have seen it earlier. I'll press the button 6. It has been gone to the initial condition. So this is my project. Thank you.